So today we have chemical equilibrium. Second part. This is the topic we will be covering. So yesterday we had introduction of chemical equilibrium. Today the second part of the chemical equilibrium. So in the second part, the first aspect what we are going to see is law of mass action. So in the second part of chemical equilibrium, the first aspect is law of mass action. So what does it say? So the rate of the reaction, the rate of the reaction is before directly proportional to the product of active masses of active masses of the substances taking part in it. So it is applicable only for reversible chemical reactions or chemical reversible reactions. So this is the part one. So this is what is called law of mass action. So it was proposed by Danish scientists Goldberg and Wedge.
Clear, sir.
Yeah, good. Now, what is active mass? Active mass, it means concentration. It means concentration. Active mass, it means concentration. That is, the concentration is expressed in moles per liter. That is called active mass. So how do we write this active mass? For any species X, it is given by number of moles of X whole divided by volume of the solution in liters. Volume of the solution in liters. So this is how we write the active mass. Noted, Amma?
Clear, sir.
Here, good. Next one. the active mass of a solid substance. The active mass of a solid substance remains constant. Since the density of the solid is constant, since the density of the solid is constant at a fixed temperature, irrespective of the amount of the substance present, irrespective of the amount of the substance present. So this is what is called active mass. The active mass of a solid substance, it is always remaining constant. So we consider the gaseous species normally for the reaction, okay, for the equilibrium reaction. It's a solid, the active mass of the solid always remains constant. It's only the gaseous species which will come into the picture in general. Okay, so for the equilibrium reactions, this active mass concept will come only for the equilibrium reactions. This is the funda what you all have to get into mind. Now, can I clear this part?
Yes, sir.
Yeah, good. Now, let us move on. Now, for the reversible reaction, let us consider a reversible reaction. A gas plus B gas gives C gas plus D gas. Now, if I write something like this, that is called concentration or active mass. If I put a bracket like this and write like this, that is called concentration of A. So now we have two things here. Rate of forward reaction. Rate of forward reaction is Kf into concentration of A into concentration of B. So this is how we write. Similarly, rate of backward reaction. See, how we write forward reaction is Kf into A into B. See, the forward reaction proceeds because of the variation, because of A and B are combining together and have some variations in their concentrations. Because of that, we are getting C and D, right? Rate of backward reaction. How backward reaction is affected? Because of C and D backward reaction is affected. Okay. So backward reaction, that will be something like Kb into C into D. And now what is Kf and Kb? They are called rate constants. Rate constants of forward and backward reactions. So Kf and Kb are the rate constants of the forward as well as backward reactions. Clear, Amma? Clear, everyone?
Yes, sir.
Yeah, very good. Now, at equilibrium, what will happen? At equilibrium, A gas plus B gas goes to C gas plus D gas. And now at equilibrium, what does the equilibrium suggest? Rate of forward reaction that is equal to rate of backward reaction. So let us call this rate of forward reaction as RF and rate of backward reaction as RB. Let us write like this. RF is equal to RB. This is what happens. So what is RF? I can write this as KF into concentration of A into concentration of B. That is equal to KB into concentration of C into concentration of D. I can write like this. Right? So please note up to here.
Noted, sir.
This happens at equilibrium. Now we define something called equilibrium constant. Equilibrium constant. What is equilibrium constant? It is, or we write it as Kc, which is Kc means the equilibrium constant when terms are expressed in concentration. Expressed in concentration terms. Concentration. So something like we have two things are there, Kc and Kp. Kc means equilibrium constant when the terms are expressed in concentration terms. Okay. So that is given by forward reaction. The rate constant of the forward reaction divided by rate constant of the backward reaction. So the Kc is given by Kf by Kb. But we have what is RF forward is Kf multiplied by A into B. Okay, right. So I can write Kf as RF divided by concentration of A into concentration of B. But remember that RF is equal to RB. That is equal to, let us say, R. Okay. Rate of forward reaction is equal to rate of backward reaction. Both are equal. And let us say that is R. So that we have Kf is equal to R divided by concentration of A into concentration of B. So similarly, I can write K backward is nothing but R divided by concentration of C into concentration of B. We can write like this. Okay, right. And now let us substitute what is Kf and Kb here. So you get R divided by concentration of A into concentration of B, all divided by R divided by concentration of C into concentration of B. Like this you can write. R gets cancelled. So when you topple the things, you get, yeah, please note up to here. Then we'll write the result. I hope you understood this, how we have done. Anyway, I'll post this video on YouTube. You can all see once again how we have done. No issues. So the first lecture, those who have missed initially, you can see that in the YouTube video. The second lecture, someone would have come little bit late. You can see that once you go through the YouTube video, I'll share that and you can all see that.
Noted, sir.
Noted. Fine. Good. Now, after toppling, what will happen? So Kc is equal to, we get concentration of C into concentration of D divided by concentration of A into concentration of B. So it is like you have product of reactant, product of the concentration of products divided by, you got something like product of concentration of the concentration of reactants. So something like this we got. So this is called Kc, which is given by, for which kind of reaction it is? A gas plus B gas gives C gas plus D gas. So when do we can write this? When we can write this? This we can write only for equilibrium reactions. So for the equilibrium reactions, this is called equilibrium constant in terms of the concentration terms. Equilibrium constant in terms of concentration terms. So equilibrium constant in concentration terms. Clear?
Clear, sir.
Very good. Now, next. So Kc is called equilibrium constant. Equilibrium constant when molar concentrations or active masses of substances are considered. Please tell me once noted. Please let me know.
Noted, sir.
Yeah, good. Now, the next point, equilibrium constant. Equilibrium constant is the ratio between the rate constants of forward and backward reactions. So can I clear this one? Hope I can clear. For an ideal gas, for an ideal gas, partial pressure is proportional to the active mass at constant temperature. So we have two types of equilibrium constants. So they are called Kc and Kp.
Clear, sir.
Yeah, good. Now, relation between Kp and Kc. What is the relation? How do we find the relation? So the relation is like Kp is equal to Kc into RT whole to the power of delta n. So I explain all the terms. So the Kp is called equilibrium constant when partial pressures of the reactants and the products are considered. And now Kc is equilibrium constant. These two will be different. Okay, equilibrium constant when concentrations are taken into account. So how do we find the relation? So that we will see.
Noted, sir.
Yeah. Now let us write this one. For a simple scenario like A gas plus B gas gives C gas plus D gas equilibrium, we will have Kc. If I have read, you know this very well, that is concentration of C into concentration of D divided by concentration of A into concentration of B. Like this we'll write. But Kp, while writing Kp, what we'll write is partial pressure of the gas C. So it is small p will write. I will change the p here little bit. So concentration of D divided by concentration, that is the partial pressure of C into partial pressure of D divided by partial pressure of A multiplied by partial pressure of B. So this is how we write Kp. So the difference you can see here, their concentrations are considered here. Here the partial pressures of the individual gases are considered. So when you consider partial pressures, you will write Kp. When concentrations are considered, we will write Kc. Please note it.
Noted, sir.
Okay, good. Now, so let us consider the general reaction. How do we consider the general reaction? Let us see. So the general reaction is like N1 into A gas plus N2 B gas. So which means that N1 moles of A is there, N2 moles of B is there. That gives rise N3 moles of C gas plus N4 moles of B gas. So all are gases over here. And now what is N1 and 2? N1 moles of, like if you have something like N2 plus 3H2 gives 2NH3. I'll tell you with an example. The N1 part is the first gas. The coefficient is 1 here. Here the coefficient is stoichiometric coefficient. These are called stoichiometric coefficient. The coefficient is 3. That means 3 moles of hydrogen is taken, 1 mole of nitrogen is taken. And now this here, N3 is the number of moles of C and N4 is the number of moles of B. And now we have delta N, a factor called delta N, that is the number of moles of products. I should say total number of moles of products minus total number of moles of reactants. Moles of reactants. So if I write that, how it looks like N3 plus N4, that is the products, okay, minus N1 plus N2. Okay, remember this is called delta N. The first factor is the delta N. Okay, this is our delta N.
Noted, sir.
Right, good. Now, so we will derive the condition Kp is equal to Kc into RT power delta N. We will derive that condition. So for that to do, let us write Kp. What is Kp? So that is, so we'll consider N1 into A plus N2 into B, all are gases. U size N3 into C plus N4 into D. So to write Kp, that will be like so Kp we have to write, that is the partial pressure of C whole power N3 into partial pressure of D to the power of that stoichiometric coefficient you had, right? N4 divided by partial pressure of A to the power of N1 multiplied by partial pressure of B to the power of N2. I hope you got it. That coefficients, whoever are there, they will come to powers. That's what, that is how you can remember. And now we know this very well, that the partial pressure of any gas is equal to the concentration of the gas, okay, multiplied by RT. This is the equation from the ideal gas equation. We know this PV is equal to nRT, right? Now I can write P is equal to N by V times RT. But this N by V factor happens to be concentration term. This is the concentration. Number of moles divided by volume is the concentration term. So that we'll write it as X gas. X gas is nothing but N by V. Clear, everyone?
Clear, sir.
Yes, sir.
Now this X gas is nothing but the concentration of the each gas. Okay, concentration of it can be anything. Okay, accordingly, let us solve this. And now Kp is equal to the partial pressure of C whole power N3 is there, partial pressure of D whole power N4 is there, divided by partial pressure of A whole power N1 multiplied by partial pressure of B whole power N2. Like this it is there. What is partial pressure of A? I told you that will be concentration of partial pressure of C is the concentration of C into RT whole to the power of N3, partial pressure of D into RT whole power N4 divided by partial pressure of A RT whole power N1 into partial pressure of B. Sorry, concentration. What I'm saying is concentration. Instead, I am telling partial pressure. Sorry for that. Concentration of C into RT, concentration of D into RT. Each partial pressure can be written as concentration of A into RT and then concentration of B into RT. Like this, we can write. Sorry for my voice mistake. And now this is how you can write. So basic, what is the basic idea? This is the partial pressure of A is nothing but the concentration of A multiplied by RT. This is the basic idea from which any partial pressure of any X is given by the concentration of that particular X multiplied by RT. So this is the basic idea from the ideal gas equation. You can write this. Right. So now we can write this as split it like concentration of C power N3 multiplied by concentration of D whole power N4 divided by concentration of A whole power N1 into concentration of B whole power N2. And now we have RT whole power N3 into RT whole power N4 divided by RT whole power N1 into RT whole power N2. So this is how we get. And now what is this term? This term is nothing but Kc, right? Got it, right? So we got this. So we have Kp is equal to Kc. And now if you have something like A power X into A power Y divided by A power Z into A power M, something like this we have. Instead of A, we have RT. So we can write A to the power of X plus Y minus Z minus M, right? Like this we can write. So we can write RT whole power N4 plus N3 minus N1 plus N2. Like this you can write. And now this, I told you in the beginning, delta N is the difference in the number of moles between the products and the reactants. So that is delta N is N4 plus N3 minus of N1 plus N2. You can write like this. So we'll replace this entire thing with delta N. So you have Kp is equal to Kc into RT whole power delta N. Remember this result, it is very, very important. This is where we'll close today. So tomorrow we continue with the next topic. This is sufficient today. Please note it. Clear, students?
Yes.
Yes, sir.
Up to this part, you please practice today and tomorrow we'll continue further. So KP-KC relationship, depending upon that, we have some more questions. So that we'll see tomorrow. Let's meet tomorrow. We'll close now. Hopefully written.